there will be a re-midterm next Tuesday evening, 6 p.m. in executive classroom, okay, which is on the 4th floor of Com 1. Those of you who got below 65 for the midterm can come again. Those of you who have more, please don't come. I'll post everything online. You can try yourself if you want to try. It shouldn't be that hard. It should be just kind of, it's actually the same kind of level as the midterm. Basically to ensure that those of you who have some things you don't understand for the midterm will figure it out. Right? That's number one. Number two is that the TAs have already built in the reminder. So someone suggested in a midterm survey that you should be automatically spammed if you do not submit your homework one day. You know, if it's 1 day left, you get spammed automatically. Someone suggested that you get spammed. So the FDI Academy will spam you 3-4 hours before the deadline automatically if you haven't done it already. Okay, so this is the second thing. This comes from, it's not our thinking, it's someone suggested it, so we put it in. The third thing is that somebody said that you don't get enough practice. What happened in the danger room? Did you get destroyed? No, it didn't get destroyed. We just got too busy. So I also now asked some of the tutors to go and create some danger rooms so that you have extra practice. Okay? So there are 1 or 2 fellas who think it's too little work, so we'll try to see how we generate work for you. But the problem here is that it also generates not work for us. Okay? Alright, so today, after the lecture. Okay. Alright, so I think we can start with some of these things. Okay, so first of all, I think it's timely for us to take a pause, okay, to remember this man. The thing that I think that is important that he said, okay, he said many things, and my whole Facebook wall is completely full of him yesterday, okay. But one thing that I think you want to think about is this thing, this quote I thought was important, okay, that we don't get a chance to do many things, okay, because I'm not sure I'm right about most things or anything at all, but I'm sure that I'm right that you're all going to die. Okay, so sad to say, I'm almost certain that you're all going to die, we're all going to die. Very likely I'm going to die before you. Hopefully I'll die before you. If not, it's very tragic. Okay, but the point here is because you're all going to die, then the question now is, I think it's important to have some perspectives as to what you're doing in your life. Right, so he says here, right, everyone should really be excellent, okay. Well, I hate to break this to you, it is not true that everyone can be excellent in anything. This is just not going to work, right? And sadly, I think some people are just not going to ace in this class or what to do. But is that a problem? Not really a problem. So what I like to encourage you to do is that you guys go figure out what is of meaning to you. And the word here is to become damn good at it, right? So so think about this, okay? All right, so last Wednesday, just Wednesday, not last, just 2 days ago, was good because you guys asked a lot of questions. But you asked a lot of questions and I cannot really finish on time, right? So I was in a rush, and now I want to quickly recap some of the last few slides from last Wednesday. So we're talking about 2-dimensional tables, okay? You need 2 keys to get a value. This is what you saw in missions 12 to 15, right? Okay, so and essentially, one implementation is use nested 1D tables. Use 1 key for 1 table, and then each table contains more tables. Okay, so this is kind of how you actually look at a problem, right? And the question was, why do we need this table thing, right? This star table star. Why? Not because that's good. Okay, so this thing is the following now. So the obvious alternative to do this, right, is to get rid of the table, star table, okay, and have a null, this is a null list to represent empty table, right? That's the obvious way of doing it, correct? Okay, so it just looks very clunky. So the question why you need this is the following. The reason why you need this is because the empty table is the object. Okay? Now, typically, how do you use these kinds of data structures? You have some kind of procedure, you pass the data structure into the procedure, right? Correct? That's what you do. I say again, normally these data structures, these are data structures that are mutable. You have a procedure that you pass inside, right? Okay. Now, so there will be cases whereby you write a procedure, you want to pass a table into the procedure, okay? And then in the procedure, you add stuff to the table, right? It comes out, what happens? Well, the table may not come out, but because you pass the table inside, you add stuff to it, the table has stuff already, right? Okay? Now, what that tells you is that you actually need a reference to the table. Now, if your empty table is the now, you pass the now pointer into the table, you won't be able to actually get it out, right? Okay, this is very subtle when you think about it. So sort of like but the point is not cycle, right? Is that you need some kind of object. You need a handle on the empty table. Okay, the now is just thing. It's not a handle. So this first, the whole point is that this first, what matters in this thing is not this table thing. What matters is actually this pointer. You want to basically pass a container around. You cannot be passing nothing. So you pass a container into the procedure, then you will actually be able to do some operations to it so that you can actually make changes. Okay? Alright. Hopefully you figure this out. If not, you'll figure it out soon enough. Okay? Next. Okay, now you have this table there, so you can use it. One example is this thing whereby you can go count words. Okay, this is simple. And the way that you do this is for this particular song, right? You want to count how many words appear in the song. You basically just use the table and update. You look at the song, cooler down the list. Okay, every time you see a word, you check the table for the word. If it exists there, you take the count, you add one, put it back. Okay, if it doesn't exist, you create a new entry with the word and count one. Okay, so this is a very simple idea. So the key idea in this particular part of the class is that you must learn how to use data structures. Okay, number one. Number two, you basically have to learn that you can build more. You can build, I won't say more complex necessarily, but you can build data structures by using other data structures. So that's why you ask you can go and implement queues with tables. Okay, and the general idea here is that you need to decide on the representation, which is that empty queue would be empty table. Okay, and then the thing what you do is that you artificially create this index, right? You can say that insert m. Okay, you insert nm where n is a number. Okay, which tells you okay, what's the unique key? What does unique key mean? It means only one copy. Okay, which makes sense, right? Because the whole point here is that a queue basically is actually an ordered set of a queue is an ordered set of elements, right? And there's some ordering. Some is early, some is later, right? So use n to represent ordering. Okay, and what you do is that when the table is created, you also create this variable called n, which tells you the head is actually 0. Okay, then as you insert the elements, you increment n. Okay, and obviously to the elements, you will basically look for the smallest element s. Okay, in the table, delete the entry and increment s. Okay, so this is for you to think about how you would finish the implementation. Okay, and then two things. First of all, use the table, create a list. Okay, create a queue, right? And then go and implement it, and then think about things like time and space complexity. Okay, so the other thing I asked you to do, and nobody did it yet, so I'm reminding you all. Can y'all go and implement tables using queues? Okay, and the question now is how would you do it? Okay, and how would you implement operations like lookup, insert using queue operations? Okay, obviously, okay, this is not an efficient implementation of tables. Obviously, you do better, right? The whole point now is to wrap your head around, you know, this idea of infinitely many solutions to problems. Okay, so suppose now you're forced to do this kind of thing, right? How would you dig your nose efficiently, or as efficiently as you can, right? All right. So think about these things, and the whole point here is to learn to think about data structures and how to execute them. Okay. Are there any questions? Okay, I'm just going through this to make sure that while I was rushing through this towards the end last lecture, You are all okay, clear? Okay, today's topic is really quite simple, so I'm not too concerned about time. Okay, we're all clear? So the last lecture was sorry about data structures, about tables and queues, and learning to create these kinds of data structures. Okay, obviously you do a lot more in 2020, and you do nastier things like ABL trees. I don't know, you do red black trees, all kinds of random nasty stuff. Okay, but at the end of the day, all these things are really what we're doing in this class are the basics, the queues, the stacks. These are the basic data structures. Okay, all right. And that's good. Okay, so today we'll go to today's topic. Okay, there's this thing called memorization. Alright, now, so let's, Sun, it's good to do a recap. This is your favorite procedure, right? Okay, so what's the time complexity of this thing? It's actually not 2, right? It's golden ratio power n, right? Okay, remember? Okay, it doesn't matter. You don't remember this. I mean, this is just, you know it's something power n, it's a nasty thing, right? Okay, and the way you see this is because this is recursion, okay, it's a tree recursion, obviously. That means you have n, okay, a problem of size n being expressed as 2 problems of size smaller than n. Okay, obviously the thing will blow up, okay, it's some kind of exponential thing, right? How much space is this going to take up? Linear, right? Okay, you know that, right? Okay. Now, the key thing to realize is the following. Now, this thing is kind of nasty, right? Okay. And you remember how you do this? You actually draw the tree, right? Okay. And the thing to realize, obviously, is that fit 5 computes fit 4 and fit 3, right? But fit 4 computes fit 3 and fit 2, right? Okay. In fact, there's still a repetition all over the place. Okay. There's something that's obvious to you, right? Okay. Very good. So it's the observation. So the question is, how can we do better? Iterative. Okay, I mean, there's this thing iterative, but later on, I like the iterative method. Huh? DP, that's DP, correct. So, but generally, the idea for me is very simple, right? The idea here is that you keep doing the same things, right? Okay? So if you remember what you actually computed before, then you can just look at the table and check. Okay, but this is different from DP, okay? We will do DP next week. Okay? Slightly different, okay? Now, so this is the structure of the table. I mean, of the computation, right? And you see that the 3 flip 2s here. Okay. Obvious way is to do what? It's just to remember what you did earlier. Okay. Now, and there's a big name for this. Okay, it's a cool name. It's called memorization, not memorization. Okay, but this is the name of this thing. Okay. Now. So the idea is this, okay? Essentially, in memorization, what happens is that you create procedures, okay, that records in the local table the values that were previously computed before, okay? So this is a simple idea, right? You have a procedure. What does it do? Procedure takes in a value, right? Means it's the input, and it copies out a value. But before it does the copying out the value, right, it does a lot of work, right? So after you do that work, what you do, you actually you keep a local table inside the procedure. You store that output value in the table, and then you copy out the value to the user. Now, the next time what happens is that somebody gives you a new value to compute, right? First, before you do any work, you check in the local table, have I done this before? If you've done this before, okay, and the computation is something that doesn't change, obviously, some computations are a bit different. Every time you compute, it's a different number. If it's not a function, it's not a kind of one-to-one mapping, you can't do this. But if it's a function whereby you compute one time, every time next time it's still the same answer, then you can do this type of thing, right? So this is a simple idea. So let's take a look. Okay? So memorized procedure essentially is something where you embed a table inside, okay, that stores various values, and you use arguments that produce as values, okay? So you use the arguments that produce the values as the keys. That means the inputs that you use to compute are used as the keys to this table. Okay, so when you call it, you check the table if its value exists. If it exists, return. If not, compute. Okay, store first and then return. Very easy, right? Okay, so it's very easy, simple idea. So look at this particular piece of code. Let's appreciate the code. So by now, you definitely must be able to look at a piece of code and appreciate how pretty it looks. So I do memorize f. So basically, I have a function f. Okay, And what I now want to do is to create a memoized version of f. Okay. Now, first thing I do is I let table. So I create a table. And obviously it's an empty table, right? Alright. Then what I do, I lambda x. Because f is a function x. Right. So this memoize f is a function, right? It's a procedure. Memoize f is actually also a procedure. In fact, it's the same procedure, except it has memoization built in. So it must be a lambda x. Okay. Now what I do, let. Okay. Previous result is what? Look up x table. Because x is the input that you come in. So I check the table. Hey, have I done this before? Obviously, the previous result will return either a value or false. Cannot find, right? This is the convention. When you look at a table, you either basically return the value or false, which you cannot find. Okay. Now, so this I do all, right? All is a bit odd, right? Why? Because all means that if previous value is not false, I will just return it. Okay, it returns true and returns it. Okay, if not, then you go to the next one. Then the next thing what I do is I let result fx. That means I compute fx. Okay. Then I insert x result into the table. So x is the key, result is the answer. I stick it in the table, and finally I return the result. Okay, straightforward, right? I'm just doing exactly what I said I would do, right? Okay, I'm using the memoized f as a kind of a wrapper around f. Okay. Okay. Now, so this thing create table. Look up. Just look up replace this. Insert. Okay, this is just the functions of the table. Now, so let's do memoization. Okay. So now that we have done memoize, right? Isn't it obvious that this is the coolest thing, right? You basically take Fibonacci, put into memoize, and all is great, correct? No. Who said no? No, isn't it obvious, right? You can remember memoize f, what I do? I take memoize, I put f. Fibonacci is also a procedure, right? I put Fibonacci into memoize, and it should all work out, right? What's the time for this? Huh? No need what? It works, right? Okay, what time complexity does this thing? Or the n? You sure? The exponential. Why? Oh no. Something's wrong, right? Yeah, so it's a problem, Okay. Now, the problem is this, right? That's the wrong way of doing it. What you need to do is to do it this way, right? That means Fibonacci was... See, the main problem is this. The main problem is that Fibonacci is this. This is fib, right? Correct? What happens is that fib calls fib, right? Well, you can memorize the fib. It's true. The problem here is that when fib goes inside, when you go into fib, right? The inside fibs are calling the unmemorized version. So basically you remember one level, right? And the rest is still kind of messed up, right? So it doesn't really help, okay? So this is a little trick here, which is that you can't just do this, okay? It means this thing is not good enough, okay? And so what you do is actually rewrite Fibonacci in this way. So you memorize here, but here, inside memorize, you need to basically go and amend it to call the memoized version of the fib, okay? And not leave it alone, because the old one will call fib, which is the unmemorized version. Okay, so it actually works, except that this is a little bit of in terms of coding, you need to be a little careful, because this is what happens. Okay? So essentially, you create this anonymous procedure, right? And you call memoize. Okay? And then you give it a name, and inside here, you modify the fib to basically call itself, so that you're calling the memoized version of the fib. Now, if you do this, it will be linear, as Richard says. How cool is that? Right? Now, why? Because you think about it, right? Every single value of n is computed at most once. So the real question is this problem is that the efficiency of the table matters. That means if the insertion takes order n, then you're in insertion deletion takes order n, then you're in trouble. It turns out that life is good. You will not know this yet. Well, maybe you know this already, but you will learn this very well next semester. We are able to do this with hash tables which would basically force lookup to become order and order 1. So you can actually do constant time insertions and removals checks on the table by using hash tables. Okay, so yes, the point now is it depends on how fast your table lookup is. Okay, if table lookup is slow, then you may not be that much better off. Okay, okay, but suppose your so question of the day. Suppose your table is slow. Insertion deletion takes order n. How bad is it? Is it still exponential or better? Think about this. Okay, so this is the question. Okay, think about it. Okay, hey, don't give me answers. Can you please post in your reflections and think about this? Okay, so this is the question. Think about. It's not. Yeah, it's not. But this is theory. In theory, it can be done, right? Okay. Now, next thing, let's take a look at the memoirs, how you analyze it. Remember, this is the picture from Wednesday, right? Okay, what's GE? Not general election. Although you all are just so excited about the last general elections, but it's not. GE stands for? Global environment. Okay. So this thing is a global environment. Okay. Now, when you do this memo fit, what happens? Okay. You have this lambda thing. Okay. Which actually, see how you do this? First thing you do is you go and do the inside lambda, right? You evaluate the inside lambda, which is this thing. You get this thing, right? You have param n. All the stuff here is here in the body. It points to the global environment, correct? Now, after that, you do what? You do memoirs, right? Memoirs is actually a lambda somewhere already, right? But you're doing now what? A procedure application, right? Of memoirs onto this thing. Okay? Now, so this is what memoirs looks like. Okay? Now, what does memoirs do? Memoirs is actually a procedure somewhere here. So when you apply memoirs to F, right? F will be this thing, correct? When you apply a procedure, what happens? You create a new frame pointing to the enclosing environment of the procedure. Okay, I haven't shown the memoirs, but memoirs is somewhere here pointing to this thing. So you create a new frame, right? Okay, and what you do then next is that you bind the F to the thing. Okay, so you bind F to the input. So F is bound here. Okay, now inside memoirs, you have this let thing. So you're now evaluating this whole piece inside this environment, right? Now what does that do? Well, actually you already know how it's done, right? Because you know that let is lambda. You know how lambdas work. So you do some stuff, you realize that, you know, what let does is that you create a new frame, okay, containing this variable, binding it to make table, which is some kind of empty table. Okay? Now, next, inside this, then what happens after the let, you evaluate the lambda, right? Correct? So the okay, the let is this thing. Inside the let there's the body. You evaluate the body inside this frame. Okay, that gives you a lambda. That points to this frame, right? Because remember, when you evaluate a lambda inside a frame, you will the enclosing environment of the lambda is the frame that is evaluated inside. Okay, so the result of this lambda x, all these things, is actually a lambda. Okay, and at the high level, what happened is that so now this is this thing, right? But then this is the result of memoirs lambda. But you need to do what? Bind memofib to this thing, so you have the memofib bound to that lambda. So after evaluating define memofib, memoirs lambda, you have this kind of a picture. How cool is that? Good. All right. If you're still confused, it's okay. Don't feel bad. Because at this point in time, about 30% of you estimated are still confused. But we have a solution to this. This is called recitation 6 or 7. I can't recall. But next week, the whole recitation is spent drawing these type of diagrams. Okay, and we'll be drawing nastier diagrams than this. Okay, you'll be many more layers. So, but after next week, you should be completely clear. Okay, but for now, just have faith that I drawn it right. Okay, and this is what it kind of looks like. Okay. So the interesting thing is this, right? You know that the memofib is now a procedure. Okay, you see, originally this is the procedure, right? Originally this was the fit procedure. Okay, and this procedure has no memory, right? I mean, there's no way to have memory, but memofib is a procedure, but what it has is that it's got memory, right? And the memory is here. Okay, what I've done is through using lambdas, I've created some memory for this procedure somewhere, and it's hiding it over here. This stuff doesn't really matter. This stuff is going to be called by this thing later on to do the right work. Okay, think about it. This new procedure is this thing. Okay, this procedure has two things. He has got memory, created here in the table, and he has got access to the old procedure, which is here. Okay? Now, suppose you execute fib3. Okay, memo fib3, sorry. That means you go down here, you do this, and you execute. Now, trust me for now that you will generate a whole bunch of frames. Okay? Again, you guys go back and try and figure out how this works, but what happens here is that when you run fib3, you will be executing this memo fib, right? Memo fib is this procedure, correct? Now, when you apply a procedure, you know that you must create what? A frame in the enclosing environment, which is here. So you create a frame called x3, right? Okay, and inside here, of course, there's more stuff, you have all the LEDs. And so after a while, you basically have this whole result. Okay, and result is what? Result is the final result. What happens here is that because the table is empty, right, you need to compute f3. Okay? Then, after that, okay, when you call f3, okay, what happens? Okay, you're a bit lost. Okay, see, this whole lambda is this stuff, right? Okay, you see on the right hand, this lambda is this stuff here. Okay, so when I call memo fib3, I will go inside here, x will become 3, right? Okay, now then I go inside there and I let previous result look up x table. Okay, so I'm inside here, remember? I mean, now I'm inside here, somewhere here. I created a new frame, x equals to 3, and now I am trying to do table lookup. Table lookup will go up here and look at the table, which is empty. So obviously, your previous result will be false, because there's nothing in the table, right? Now, if the table result is false, I will do another let, right? I'll let result be fx, okay? Which is f3, obviously. Okay? Now, then what happens is this, I will insert x result in the table. Okay, so basically, remember, there's the x3, previous is false, because cannot find. Then I'll do a let f3, let result f3. Okay, so what does this do? f3 will go up here, find f, okay, and compute the result. Okay, now, and then f3 will do what? We'll call f2, right? Okay, and essentially you compute the result. Okay, and then f1 will also do the same thing, you compute the result. Okay, now then after what happens is that you basically will you will basically okay, actually this is a little bit. Okay, the truth is that the second time it's no longer f2, right? It will be memo fib2 because you have modified the so I'm a bit sloppy here. So the fact is that the f is actually this thing. Okay, f is actually this thing. All right. So this thing is f, right? So this you will then call memo fib, which is actually that's why you get 2 and 1 here. Okay. Now the thing is that when you reach 1, okay, what 1 does is this. When you compute 1, okay, when the result comes out, right, you will then insert the results x into the table. So basically the table is updated. Okay, remember, because what happens is that the scheme is applicative order, right? So that means when you compute 3, you go inside here, you compute 2 first. Okay, that means the return result, result's not returned yet, right? Because then 2 will be a recursion call inside. Okay, you compute f1, right? Or memo fib1. Okay, so the point, but 1, obviously, 1 is the end, right? Because 1 is the base case. Okay, so when the base case returns, okay, so this is returned as a base case. It returns the answer. Then what happens is that you will be called, the insertion will be called, because then it will go up to the next level. Okay, and the memorization thing, this becomes f, the result becomes a 1. Okay, and then you will then insert the 1 into the table. So what a table contains is that is 1 1, which means that f1, the result is 1. Okay, so the f is then returned to f2, right? So f2, okay, well, okay, sorry, then f2 will do what? f2 compute f0, right? Okay, f2 computes f1, f2. F2 computes f1 and f2. F2 computes f1, f0. F1 got computed. Okay, answer is 1. Then return, and then the table is filled. Next thing, you compute f0. F0 will give you 0 plus base case, and then you return the result. And then for that, if you return the result, you will actually insert the table. So you get this. Okay. Now, then after that, these two results return to the f2. F2 will add the two together, return the answer, but the memorization part will actually take the answer, insert the table before you actually return the answer. So you have to update. Okay. Now the F2 is what? F2 is returned to F3. Now, so F3 does this. F3 is F what? F3 is F2 plus F1, right? So F2 has finished computing, insert the table, return the answer, which is F2 will be 1, right? Sorry. Okay. Then now you go to compute F1, right? Now, but F1 now is different. This time when you compute F1, do all computation and stuff. Now when you compute F1, what happens is that you will do what? You will actually go into the table, do a lookup, and you realize that previous is now 1. Okay. So basically this will return and will give you the answer. So let's quickly look. So what happens in the evaluation tree is this: fib3 will call fib2. Okay. Fib2 will call fib1. Okay. And then it will memorize it. It means it will complete. Fib1 is a base case, it returns answer, but because it's memorized, before it returns answer, it inserts in the table first. Okay. Now then this answer, which is fib1 is 1, right? Fib1, the 1 will be returned to this computation. You have plus, you have now fib0. Correct? Again, fib0 is base case, so it returns 0, but before it's returned, it's memorized, which means it's in the table. Okay. Now with 1 and 0, you know that you can compute 2, right? You just add 2 together. So this guy will then return you fib2 which is 1 okay, to fib3. Correct? Fib3 will call what? Fib1 because the fact is that fib3 is fib2 plus fib1, right? So you just memorize first, then call fib1. But now fib1, right, no longer computes anything anymore, because fib1 has already been memorized here. So now it will just find a table and return answer. Okay? And then once it does that, fib3 will be memorized also. Okay? So the point here is that in the computing fib3, you will go down, compute these computations, you actually insert how many values in the table? Paraf, how many values? After you finish computing fib3, how many values do you insert in the table? 4 values, right? Okay, can count. Alright, so that's all. Very, very straightforward. Okay, now let's try another example, which is choose K. Okay, you all know what choose K does, right? Choose K is basically to given K n objects. Okay, how many ways are there of choosing K sets? Sets of K distinct objects. Okay, obviously you know there's a formula, right? Okay, but suppose you don't do it by formula, you can obviously do it by using a recursion, right? Okay, how does it work? So choose K, first of all, if K is more than n, no possible, right? Because you can't create bigger subsets from n elements. So the answer will be 0, right? When K is more than n, the answer is 0. Okay? Next, okay, if K is 0, it means choose nothing. There's only one way of choosing nothing from n elements. Okay? Now, if K is 1, means what? Choose everything. There's only one way of doing it, right? Okay? So these 3 base cases are kind of obvious. When K is too big, you can't do anything. When K is 0 or K is n, you can only do one thing, right? Now then the recursion. How does recursion work? Well, again, this is similar to which problem? Count change, right? So basically the way to do recursion is this. You take this element, okay? If you take the first element, then you have how many elements left to choose? K minus 1 elements, right? So if you take if you choose the first element, you have altogether n minus 1 choose k minus 1 ways of creating sets of the element. But there are two ways of creating this type of combinations, right? One is you choose the first element, one is you don't choose the first element. So if you choose the first element, you will have n minus 1 elements left, out which you pick k minus 1 left. The other possibility is you don't choose first element, which means that you have only n minus 1 choices, and you need to pick k of them. Okay? So the similar logic that you have for count change, you apply here, you'll be able to get a recursion for n choose k. Okay? Yeah. Now, so this is the logic. Okay? Again, okay. Some people want to know how to do out in this class. The way to do out in this class is actually basically not to remember answers, but essentially to sort of remember this kinds of high-level ways of thinking about stuff. Right? So we are applying the same sort. So this is not the same problem as count change. But the key thing is to be able to do count change, do this one, and later on if you see similar kinds of problems, right, apply the thinking. Okay. Now if you try to look at thing, okay, so don't look at new problem, think it's similar to count change, and next thing you do is try to memorize the code. It's quite a disaster. Okay. Two things. The whole class is about two things. First thing is about how to solve problems. So at high level, you need to look at a problem, figure out how to think about it. Okay. The second thing is that given the kind of strategy that you choose, okay, you must figure out how to convert the code. Typically, the second way is the second part is easier. Typically, unless your first part is really nasty. Okay, means if you have good and bad, there are infinite many ways to solve problems. Okay, the challenge will be is that so I say again, the two skills are: first skill is figuring out high level how to solve the problem. Second skill is converting the first part into code. Okay, and these are two competencies you need to actually figure out. Now, I've shown you some examples in class. Those examples, the way to solve it is very elegant and very simple. The converting the code is completely trivial, right? Okay, correct. It turns out that the first way, the first case, there are often many ways of solving the same problem. If you choose a really nasty way of doing it, the conversion can be very nasty. Makes sense, right? Okay, so just remember this kind of. So basically, what happens is this: you need to be very proficient at converting algorithms to code. So much so that when you think of an idea, right, you should be in your head, be able to figure out how nasty it is. And if you do my exams, you know confirm the answer is 5 lines or 7 lines. So if it's very nasty, there must be another way of thinking about it. Okay, so you should try to think harder to see whether you come up with another way of solving it. And the reason is this: the simpler your approach is, the less nasty your code is. It means fewer lines, the less you have bugs. I mean, that's right. The more lines you write, the more likely you have bugs. Okay, so you need to understand this very carefully. Now, so this is wait. Okay, what's the order of group for this thing? Nasty, okay. How do you spell computation? Memorization. Very good. You learned something. Okay, cool. How easy, right? Okay, now, so you can actually do this. Okay, this is what you write a table, memorize, do this. Okay, but obviously very nasty, okay. So this is one way of memorizing the choice, which is really nasty, okay. So obviously you remember this thing, right? Okay, just saw it like a moment ago. So obviously you can then do this, right? Instead of having, one f x, you have f x y, right? So this is what you can do to do a two-way memorize, okay? Now, once you can do this, obviously you can do this, right? Alright? Yeah. Okay obviously cannot, right? Just seeing whether you pay attention. So this is obviously wrong, even though it looks obviously obvious. Why? Because you will call old version. If you do this thing, it's kind of at the first level, okay, but you call the wrong version, right? So essentially you need to go and rewrite it this way. You need to do the same thing that you did for the other version, flip, okay? So essentially it's the same thing. I mean, the code is completely the same, okay? The only difference here is that you have inserted this particular thing here to do the memorization, okay? And you have replaced this to refer to self so that it calls the memorized version instead of the old version, okay? What's the order of growth? Order n, I see order n k times k or something, okay? Because the general idea here is to realize that a bit like what you just said earlier, there's a table somewhere, and when you compute n to k, you are saying the k, the whole table. The table is the size n times k, right? Pretty much around there. Okay, so question today, okay, again, change what's our growth? Can you use memorization to compute? If no, why? If yes, what's the order of the growth? Okay, and go and implement a 2D table for kicks. Okay, so again, the things asked to do basically is not very hard problems, but it's meant for you to practice. Okay, so the hardest problems are the latest path should be quite straightforward. I already told my tutors to tune it down. Okay, the last time they ramped up for two, 3 lectures to prepare you mentally for the midterms. Midterms is over, so you can chill out a little bit. Okay, hopefully a good weekend. Okay, and so this is the key takeaway. Memorization, okay, can dramatically reduce computations. Is it free? No, why not free? Free what? We're going to take out space, So we are trading off space for speed, which is okay because memory is cheap. Okay. Last time, don't laugh, no. When guess how much memory my first PC had? 64 kilobytes. Excellent. That's Apple. Okay, in memory of Jobs. So and then obviously your Bill Gates said, right, 512 is more than enough, right? Yeah. So 6 is so now today you don't care. Okay. Now, so the thing is this: when the value is computed, you need to remember the table. Okay, along with the argument that produces it. Okay. Next time, very simple idea. Next time you call the procedure again, you check whether it's done before, right? If done before, then you return the answer. If not, then you do and put it and store the answer. Okay. So once you have this, okay, the key thing to understand is this: how do you know the order of growth? In this case, you just count how many times you compute how many times you compute the thing, okay? And choice will do how much? N times k, right? Okay. Okay. So pretty much today is a kind of short lecture because it's really quite straightforward. Right, it's just about figuring out this simple idea that if you this is general idea. General idea is this: you see some nasty, you see a nasty exponential tree computation. Okay, the observation you need to make is that many of these nodes are the same. Okay, once you see that many of these nodes are the same, the natural thing to do here is to go and only compute each thing once. Right, and what that does is that it prunes off. Okay, what is really happening here is this: the normal computation is a tree, right? Okay, but many of the nodes are the same. If the nodes are the same, it means that the rest of the tree are also the same, right? So what memorization does is actually a tree pruning operation, which is that essentially you prune off many of these branches, leaving you only how much? It's actually a linear number of nodes, right? Okay. Because each value can only be computed one time. Okay? So that's about it. And all you need to do, the other key lesson here is to be careful that when you do this memorization, you don't go and call the unmemorized version of the procedure, right? Because then you basically have to do some modifications to call the memorized version so that you can remember stuff. Otherwise, it makes no sense. Otherwise, you memorize correctly, but only one level, then everything else you redo. Okay? Any questions? Okay, if not, then go back home, weekend, build your robot. Next Friday will be a robot contest, very fun. You can check online, and this is one thing that appeals to the guys because it's very violent, right? You're trying to basically destroy the other guy. How cool is that? How many classes NUS encourage violence? Okay, I'll see you guys next week. Thank you very much. one is depends on you.
So whatever.
The main problem is that you want to do yeah, correct. So basically, if you can find here, then you're done already. You cannot find here, you go up there, you find there. Until you cannot find it.
So why does this lambda need two arrows?
Because one arrow points to the code, one arrow points to the environment.
Why can't it just create a box for the body?
It just doesn't do that.
Okay, to distinguish the lambda is
it's not same. This is a random thing. It's different things.
Why did the square is inside this global environment? Yeah. Lambda is outside.
You go to
So for procedures that defined by define, they're storing the global environment.
No, it's not stored. Procedures are not defined by define.
The name is stored. The name of
define, okay, see, the two things define, right?
Connect the name with
you connect the variable with the value. The value is a procedure, the value is a number. So in this case,
it's not a name with a procedure. It's a name with
something
value.
Yeah.
Then
but lambda returns a procedure, so this is a value that you define.
For example, you define square as this. Actually, you create
this thing doesn't create a lambda, right?
Yeah. When you evaluate it,
so define, when you evaluate this lambda, you create this thing. And then define is you just bind this thing to this thing. So you can do define square 3, right? You can tell 2.
It's just
then the square becomes 3. So the define and the lambda are different things. The lambda creates
let me rephrase it. When you define, you create nothing. You just bind this square to this procedure.
No, you find may not procedure, maybe something like whatever. You find to the value. This is the value, right?
But if you do not evaluate, then there's no value.
But you evaluate this because you define, you evaluate the value, and then you find something.
For example, if you evaluate it's a procedure, it returns
this. Yeah, correct.
In the document. Correct. So you bind it to this.
Correct.
Okay. Then when you evaluate square something,
you apply this.
You apply this and create an environment.
Frame.
Create a frame. Then you compute it and then return the value to be bound.
Whatever. Yeah.
Then this square actually is identified.
No, the square is not done much. You next level already. You call square something, you find it in algebra.
Because in the very first lecture you said define is like this.
Yeah, correct.
These are the names, these are the values.
Correct.
So this is different from the environment.
Same lah. This is inside here. Same thing.
This inside here.
This two is same thing, right?
That is the environment.
Yeah, it's environment. Same thing, right? I mean, I can instead of drawing this thing like this, I can draw a whole table like that, right? No difference. Square is so square, and then this
and the procedure.
This one.
Okay. Then square 5, the key is 5 or the key is square 5? Because now you get a specific value. You need to store it.
No, the square 5 has no storage.
It's just the return the value. Okay. So